Welcome to another unit in business mathematics. This time I'm going to talk about so-called inverse matrices. So in the previous sessions we talked about how we can add, subtract or multiply two matrices. So there's basically only one thing left, and that's divide one matrix by another. The problem with this regard is, well, you cannot really divide one matrix by another, but we can go like a roundabout way, as with normal numbers, where when we say we divide by 5, we can also interpret this as we take the inverse of 5, which is 1 divided by 5, and we multiply the original number with this. And well, 1 divided by 5, that's nothing else than 5 to the power of minus 1. That's basically what we're going to do here. We discuss how we can get, for a specific matrix, the matrix to the power of minus 1, which we call the inverse matrix. And well, the inverse matrix in general is defined as the matrix as if I multiply my original matrix, here A, with this matrix. In particular, it doesn't matter whether I multiplied from the left or the right. In both cases, I will get again the identity matrix, the unit matrix. The important aspect here is, well, this can only work similarly from the left and the right if I actually work with quadratic matrices. So in other words, my matrix A first off needs to be quadratic so that I can even determine an inverse matrix. Also, there are other regulations. The best one to go with is if we calculate the determinant of a matrix, this also has to be different from 0. If it's 0, it's not possible to invert our matrix. Well, with those comments, we can then actually start in the discussion on how we proceed to calculate the inverse matrix. And in the end, it's relatively simple. We take the matrix we have, and then we expand this slightly by writing down first this matrix. Then, as with the Gauss algorithm, we do a vertical line, and to the right of this vertical line, we write down the identity matrix. So we're more or less again saving a linear system of equation, but the right side is not a specific vector, but the identity matrix. Well, what do we do then? Well, we simply applied a Gauss algorithm so long as it takes for us to get on the left side our identity matrix. So we're basically solving this linear system of equations. And here we have the same rules as with the Gauss algorithm. Switch to rows, multiply or divide one row with any real number except 0, and add or subtract a row from or to another row. And well, the problem here is, well, I said we can only invert invertible matrices. We can check this with the determinant. If at this point you don't know how to actually calculate a determinant, doesn't matter, because in this case you can also get an idea whether this will work out fine or not, because once on the left hand side you only get zeros in one row, you know this matrix is not invertible. So that's an additional checkpoint for you to know, okay, at this point stop, don't have to proceed, this is not invertible. Well, that's basically then all there is. So if we take the matrix we had on the slide before as an example, first step we can do here to make this a bit easier is multiply the first row with 1/2, or rather divide it by 2, making it a bit easier to proceed, because then we can simply subtract the first row from the second, giving us here this result. This already has upper triangular form on the left side, which is actually the first step of the Gauss algorithm. So the only thing left to do for the second step, getting ones on the diagonal, would mean here I have to divide the second row by -2, or rather multiply it with -1/2, which then would result in this part. We see we are almost finished. The only thing which actually keeps the left-hand matrix from being the identity matrix is the 1 in the upper right. And we can get rid of this one by subtracting the second row from the first. Then on the right side, we just have 1/2 minus 1/4, 0 minus -1/2, giving us in the end this result. So on the left, we have the identity matrix, and the matrix we have on the right, so the 0.25, 0.5, 0.25, and minus 0.5, that's now our inverse matrix. So if we were to multiply this matrix with the original matrix A, independent of whether we go A times A minus 1 or A to the power of -1 times A, in both cases we would get the identity matrix as a result. Well, that's already all there is regarding inverse matrices. So I hope you enjoyed this session. And well, I say goodbye and see you next time.